Hello and welcome to another video. In this video, we will look into the modeling of a circuit which has a DC generator in it. So a practical example of modeling of a system which consists of a DC generator. Before going into that, let us see what a DC generator is. A brief introduction of DC generator. A DC generator is an electromechanical device that converts mechanical energy into electrical energy through the process of electromagnetic induction. The fundamental working principle of a DC generator is based on Faraday's law of induction, which states that a voltage is induced in a conductor moving through a magnetic field. Some of the key components of a DC generator include armature, the rotating part that cuts the magnetic flux and induces voltage, field windings or permanent magnets, generates a magnetic field in which the armature is rotating, commutator, a mechanical switch that converts the alternating current induced in the armature to direct current, brushes, provides the electrical contact between the rotating armature and the stationary electrical circuit. So DC generators are commonly used in various applications which requires low voltage, also battery charging, etc. The operation of a DC generator can be broken into the following steps. So magnetic field interaction. In a DC generator, we have the permanent magnet, or we will use some circuit like called as exciter loop to produce the magnetic field. And this is the armature. So this armature is a conductor that is placed within this magnetic field. And once this conductor is mechanically turned, an EMF is induced. That is how we generate voltage. Now, which is generated here is AC. To convert that AC to DC, we will use these commutators. According to Faraday's law of electromagnetic induction, we know that when a current carrying conductor is placed in a varying magnetic field, an EMF is induced in the conductor. By Fleming's right hand rule, the direction of the induced current changes whenever the direction of motion of the conductor changes. Let us consider an armature rotating clockwise and a conductor at the left moving upwards. When the armature completes one half rotation, direction of motion of the conductor will be reversed downward, and hence the direction of current will be alternating or changing. So we will be producing an AC here. Then a split ring commutator, so this split ring commutator, connections of the armature conductors gets reversed when a current reversal occurs. We can get a unidirectional current in these terminals. Now the DC output, the output EMF is proportional to the number of rotations and the magnetic flux. This magnetic flux again is equal to the current in the exciter loop multiplied with the number of stator turns divided by the magnetic resistance. So we will require this formula while deriving the electrical circuit. Now with this basics on the DC of DC generator, we will see an example which has a DC generator in a circuit and how to derive a model of that circuit. Now this is an example of a circuit which has a DC generator. So the voltage is generated across DC generator and name it as UGI. Now there are two sections. The first section is to the left, which is nothing but the exciter loop. And the second part is on the right, which is the rotor loop. Now the exciter loop, there can be many ways by which you generate the magnetic field. So here we are using an exciter loop to generate the magnetic field, and the voltage, input voltage is V1, and there is a resistance Rs, which is the stator resistance, and L is an inductor. For this loop, when you use the Kirchhoff's laws, we can write the equation of this loop as V1 of t, the voltage supplied at the input, is equal to the voltage across this resistance and the voltage across the inductor. So Rs I1 of t plus L di1 by dt. Since the voltage across the inductor is L, di1 by dt, and I have written it on the right top. We will use this equation later. Now, like I explained earlier, the EMF generated will be equal to, the EMF generator will be equal to some constant C multiplied with N. N is the number of rotations multiplied I1. I1 is the voltage supplied to the exciter loop, voltage in the exciter loop, and N is the number of stator turns divided by Rm. Rm is magnetic resistance. So this is the voltage generated by the generator. Now, second loop, in the rotor loop, this V2 is the voltage that is required for us. That is our state. So our desired output is the voltage V2. Now I'm considering that as a state is equal to RD into I2 of t. I2 is the voltage in this, sorry, the current in this loop. So that is equal to, current in the loop is equal to the voltage UGI, supply voltage, divided by RR. RR is the resistance of the rotor. This is the resistance of the feeder, the lines, and this is the resistance at the load, RD. So I'm substituting this voltage equation here, and I get RD into CNI1N divided by Rm whole divided by RR plus RF plus RD. So considering all other terms except this I, all other terms are constant. So I can take it as some constant multiplied to I1 of t. Now x of t is equal to k into I1 of t. It's nothing but I1 of t is equal to x of t divided by k. Now we will substitute this back into V1 equation. So after substituting this I1 of t in this equation of V1, we will get as Rs into x of t divided by k plus L by k dx of t by dt. Keeping this, taking this to the left side and taking V1 to the right side, we will get, taking dx of t by dt to the left and V1 of t on the right, we will get this equation. Dx of t divided by dt equal to minus KL Rs x of t plus k by L V1 of t. So V1 of t is nothing but our input u. So this is in the standard form that x dot equal to Ax plus Bu, where A and B are constants. So the state x and the derivative of the state x dot and the input u. So this is the model of this network. So we have seen an example where DC generator is a part of a network and derived the model of that network. Thank you.